So we started the Jordan canonical form. Just to remind you what we discussed last time, the goal here is that having a linear transformation, a linear operator from a space from C7 to C7, to find a basis for the space V such that the matrix of T in that basis looks like this here, which is called the Jordan matrix. These are Jordan blocks. So basically what we're looking after would be those kind of blocks arranged on the diagonal. A Jordan block would mean a single number, like here. Or if you have more than one number, the matrix should be upper triangular with just ones on top of the main diagonal. And everything on the main diagonal should be the same, should be equal, right? So that you have the same number on the main diagonal. So this is what we're after. It will turn out that any linear operator whose characteristic polynomial splits will have this property. That is, there will always be such a basis, which will be called the Jordan canonical basis, such that the matrix of T in that basis will look like this. So we started looking into the properties that such a basis would have. So first of all, we noticed that because the matrix of T in that basis looks like that, it's characteristic polynomial. It's very easy to be found, right? It's just going to be this one here. The eigenvalues of the operator T are nothing but the entrance, the entries from the main diagonal, right, of that matrix. So 0, 2, 3, and 4. But then we notice that those entries from the main diagonal don't actually tell everything about Jordan blocks, because here is another operator with the same eigenvalues and therefore the same entries on the main diagonal, but clearly the blocks are completely different. So this one pretty much has 7 blocks, little blocks, 1 by 1 blocks. The one above had less blocks. All right, so now going back to this operator T on top there, we notice that because of that 3, which shows up by itself in the first column, then T of V1 is 3V1. Therefore, V1 is an eigenvector of T corresponding to the eigenvalue 3. And similarly, V3, V4, and V7 turn out to be eigenvectors, right? But not all of them are. So the missing ones, which are V2, V5 and V6, don't have that property, because if you look at V2, T of that is given by the second column here, right, of the matrix. T of V2 will be 1 V1 plus 3 V2. So V1 plus 3 V2. But we were able to rewrite it like this. And then applying T minus 3 identity again, we got 0. Right? So the idea is that whenever a vector is an eigenvector, this thing holds, right? Because T of V1 is to move the 3V1 to the left and rewrite that as T minus 3 identity of V1, you get 0. Same for V3. It's corresponding to 4, so T minus 4 identity of V3 is 0. V4 corresponds to 2. And V7 corresponds to 0, so T minus 0 identity, V7 equals 0. Right, so T minus lambda identity, where lambda is the eigenvalue, applied to the eigenvector would give you 0. Which is not the case anymore for vectors like V2, V5, and V6, but what happens here is that T minus lambda identity squared for V2 turned out to be 0, squared still for V5, but cubed for V6, right? Those were not, but still something pretty nice happened there. So we said that in general, if lambda is an eigenvalue, this kind of relation needs to hold, right, for some p. If p is 1, then you get the eigenvectors, right, the ones from above. If p is not 1 and it's higher, you get all the other vectors in the basis. So that's pretty much what we discussed last time. So let's continue. So now, if lambda is a scalar, so I'm not assuming it's an eigenvalue, and x is a vector such that this holds for some positive integer p, then we're going to call x a generalized eigenvector. So what does that mean? It means that if p is 1, p minus lambda identity of x is 0. So in particular, p of x equals lambda x, right? So lambda will end up being an eigenvalue. And x an eigenvector corresponding to lambda. But p doesn't have to be 1, right? Because it says in the definition above, for some positive integer p. If p is something other than 1, greater than 1, well, if p is greater than 1, so that means it's at least 2. I can write something like this. I pull one of those t minus lambda identity out, and that gives me t minus lambda identity of t minus lambda identity to the power p minus 1 of x equals 0, right? So if I call this vector y, then t of y is lambda y. So lambda is again an eigenvalue. So no matter what the value of p is, that scalar lambda will have to be an eigenvalue if x is what we define to be a generalized eigenvector. So pretty much lambda is an eigenvalue and x could be an eigenvector or more than that, right? So the eigenvectors are automatically part of the generalized eigenvectors, but there are more such vectors in there. Okay. So we're going to just collect all those generalized eigenvectors, put them in a set, and call that set K lambda. Okay, so K sub lambda is called a generalized eigenspace of T. It contains all those vectors x such that T minus lambda identity to the P of x equals 0 for some positive integer P. In particular, for p equals 1, that would give you again the original eigenvectors, not the generalized one. So in conclusion, what we called before E lambda was the eigenspace, right, for lambda. So the eigenspace is just a special case here, is obtained, all those vectors in the eigenspace are obtained when p equals 1. But again, K lambda may contain more than that. Okay, so let's look a little bit into the properties of this generalized eigenspace, as those would be actually the key to constructing the Jordan canonical form of an operator. So here are the properties that they have. So now, what I'm going to try to do in this section, this is a very, very long section with a lot of proofs, and I can't even attempt to prove all of them, so I'm not going to do that. What I'm going to do is to just give you enough results and enough proofs such that it makes sense to do what you'll have to do in the actual applications, you know, so for you to understand what's going on without proving everything because it's not doable. So theorem, lambda is an eigenvalue. I'm going to prove this one. K lambda, the generalized eigenspace, is in fact a T-invariant subspace of V containing E lambda. The fact that it contains E lambda, we've already noticed that. So let's see now that it's a subspace. Part B here is just a technical result that is needed in later proofs, so I wouldn't worry too much about that now. Okay. So lambda is a subspace. Okay. Now, how did we prove that a set was a subspace? Three things, right? Zero needs to be in there, closed under addition, and closed under scalar multiplication. So is the vector 0 an element of K lambda? Look at the definition. The definition of K lambda says that T minus lambda identity to some power P of the vector 0 should be 0. But T minus lambda identity is linear, right? Raised to any, you can just let P equal to 1. A linear operator applied to 0 gives you 0 anyways. Closed under addition. So x and y are two vectors in K lambda. That means for some P, T minus lambda identity to the P of x is 0. And because y is in there, maybe you have another integer like q. Such that T minus lambda identity to the q of y equals 0. Okay, but now I want to find an integer, a positive integer, such that that power of T minus lambda identity, when applied to x plus y, will give me 0. Well, everything is linear here, so whatever power I choose, it breaks into that sum, so it has to be a number such that when applied to both x and y would give me 0. So what do you think that number should be? X works with that number p, right? Y works with the number q. Anything bigger than the max between p and q would work. So let me put p plus q. So I'm not worried about which one is bigger or anything. Why does this p plus q work? Because for x I want to use the p power, so I can break it like this. That's how I get p plus q power after all. And for y, I'm going to do it backwards. T minus lambda identity of the p of x was 0, but then any linear of 0. Yeah, the last one is y, thanks. Similarly for y, so t minus lambda identity to the q of y is 0. And again, any linear operator applied to 0 gives you 0. So in the end, you end up with 0. So closed under addition, closed under scalar multiplication. So because x is in k lambda, p minus lambda identity to some positive integer power p of x equals 0, right? What do I do with c times x? Well, that thing is linear, so the c can be just put in. I'm just going to multiply by c, both sides, and then move c inside. And I get that it works for the same positive integer p as x had. All right, what else do we need here? So it's a subspace. We've seen that it contains E lambda. It's also claimed to be T invariant, so let's look into that. So you start with an X in there. We want to show that T of X is also in there. So all we know about X is something like this. Some value of P in N, T minus lambda identity to P of X is 0. So what I'm going to do is to apply T to both sides. The right side would still give us 0. But here's what happens on the left side. This is T composed with T minus lambda identity, right? P times. That's the left side. So when you do T of all that thing, it's in fact T of this, and so on. Right? So here is what happens when, let's just go from step to step. Like if I only had one of them, so if P equals 1, and I want to do T of T minus lambda identity of X. What is this? This is T of X minus lambda X, right? T is linear. T squared of X minus lambda T of X. Correct? But isn't this the same as this? This is the same as the operator T minus lambda identity applied to T of X. What I'm trying to say is that T minus lambda identity and T actually commute as operators. You know that that's usually not the case, but because, you know, T and T minus lambda identity are kind of close together, they end up commuting. So that means this T from here can be moved in between here, but then it commutes with T minus lambda identity, so I can move it again, right? So I keep on moving it until the very end. So this is the same as T minus lambda identity to the P of T of X. All right, I just moved it all the way to the right in here. Okay, but this was 0. This is 0. So here's what happens. T of X is in fact a vector with a property that there exists some P positive integer such that T minus lambda identity to the P of that vector equals 0. But that's the very definition of the generalized eigenspace. So the underlying equation there just tells me that T of x must be a generalized eigenvector. So that's exactly what we wanted, right? To show that K lambda is T invariant. Okay. So K lambda is a subspace, is T invariant. What more? In terms of its dimension, here's what happens. If lambda is an eigenvalue of multiplicity m, then dimension of K lambda cannot exceed m. And more than that, here is how you find K lambda, the null space of T minus lambda identity raised to the power, which is the multiplicity of the eigenvalue. And here maybe you should see a connection with the eigenspaces E lambda, right? Remember that in the past, in chapter 5, we proved that the dimension of was less than or equal than m, the multiplicity of the eigenvalue. And to find E lambda, all we had to do is to find the null space of T minus lambda identity to the first power, right? It was back then. Now the generalized one we've seen that E lambda is a subset of K lambda. Correct? We've seen in the previous theorem. But still, according to this theorem, it turns out that, first of all, being a subspace, this kind of relation must hold, so the dimension of E lambda is less than or equal to the dimension of K lambda. And according to Parts' theorem, this is still less than m. Okay? So it sits in between, kind of. Okay. So K lambda was a T invariant subspace, right? Whenever I'm dealing with a T invariant subspace, I can take the restriction of T to that subspace and it's going to become a linear operator. And more than that, we've seen that the characteristic polynomial of the restriction of T to any T invariant subspace like K lambda divides the characteristic polynomial of T. Right, that's part of chapter 5 or 6, probably. We've seen that before for any T invariant subspace, so in particular here. So let's call the characteristic polynomial of T restricted to K lambda P of T. And let's denote by D the dimension of K lambda. We're trying to show that this dimension is at least m, m being the multiplicity of lambda. What we show is this. We show that the characteristic polynomial of the restriction looks like this. It is exactly this one, -1 to the power d times t minus lambda to the power d. This is it. That will be the characteristic polynomial of the restriction. Because this one has to divide the characteristic polynomial of t. Well, I don't know what the characteristic polynomial of t is, but I know for sure that it's going to look like this. T minus lambda to the m times something else, right? M being the multiplicity of lambda. Because it looks like this, and this one divides it, there is no way that power of d can exceed the power of t minus lambda on the right, which is n. So if we can show that the characteristic polynomial looks like that, we're done, right? This is all we need. Okay. So, how do we show that? Well, first of all, the restriction to k lambda should have lambda as an eigencharacteristic polynomial looks like that. So why is lambda an eigenvalue? Well, when you restrict to tk lambda, then t minus lambda identity to some power p of x has to equal 0. And we've seen this idea before. You pull out one of them, that leaves you with p minus one of them. So the same idea as before, that this makes lambda an eigenvalue and y an eigenvector. Okay. So lambda is an eigenvalue, so t minus lambda is a factor, right? Remember that the characteristic polynomial of t splits, so the characteristic polynomial of the restriction splits, so I'm allowed to factor it out completely, right? I know that one of the factors is t minus lambda to some power, but if I can show that there is no other factor, then I'm done. It has to be that. So if mu, let's say, would be another factor in that polynomial, then mu is another eigenvalue for the restriction. And t minus mu identity of some vector x is 0, x being in k lambda, because that's being an eigenvalue means, right? So t of x is equal if mu is an eigenvalue. Okay. But let me go back a bit to here. If mu and lambda are different, then t minus mu identity restricted to k lambda is in fact 1 to 1. What does this mean for us? One to one means that the only 0 that it has happens as 0. So x has to be 0. However, that doesn't make any sense because we said that mu is an eigenvector, so an eigenvalue, so x would be an eigenvector. An eigenvector, by definition, cannot be 0. While the previous, that's the only thing that can happen. So it's definitely not possible. So tk lambda has no other eigenvalue, hence its characteristic polynomial. It's only this factor. It is completely, factored out. It splits. D is the dimension, so it has to be of D. If 1 to the D is from the format, right? When you compute a characteristic polynomial, when you subtract things off the main diagonal. Okay. So the dimension of k lambda is at most n, based on all this. That was part 1. Part 2, again essential, how to actually compute k lambda, okay, as the null space of t minus lambda identity to the mth power. Okay, let's prove that. We're going to do that by double inclusion. Let's see this first. So if we start with a vector in the null space of T minus lambda identity to the M, that basically means that T minus lambda identity to the M of that vector is 0, right? But K lambda was defined to be the collection of all those vectors Y such that T minus lambda identity raised to some positive integer of that vector. So in particular, the value of P in the definition, if it's equal to M, that will give us that Y is a generalized eigenvector. Okay, backwards. Next in K lambda, which in particular means that T minus lambda identity to some positive integer power P of X is 0. But we want to show that X belongs to the null space of T minus lambda identity to the M, M being the multiplicity of lambda. That is, we want to show that T minus lambda identity when raised to the mth power and applied to X would give you 0. Okay. And we're going to do that based on the characteristic polynomial of the Hamilton. Remember that according to Cayley-Hamilton, a linear operator satisfies its characteristic equation. It was the characteristic polynomial of the restriction to K lambda. So T, my quantity of X equals 0 for any X in K lambda. And D, we've seen, it is at most M. This -1 to the D really doesn't matter, right? It's just it's something that equals 0 in the end, so it doesn't influence anything. Okay. And I'm applying this to vectors in K lambda, so I can just rewrite it like this. T or the restriction, it doesn't matter what I write because I'm still applying to vectors in K lambda. And D is some number less than or equal than M. But if D is less than M, then I can keep on applying T minus lambda identity to both sides of this equation as many to raise the degree to M. Okay, so if D would be M minus 1, let's say, by applying T minus lambda identity again to both sides would give me T minus lambda identity to the M on the left, T minus lambda identity of 0, which is 0 on the right. Just apply it again and again as many times as you need to end up with that. So the essential thing here was that D was less than or equal than M. Okay. So, what do we know so far? So we know that that value, we can construct this generalized eigenspace whose dimension is at least, right, the multiplicity of lambda, and that could be computed by taking the null space of T minus lambda identity to the M. Now, I was telling you that those would be the key to construct the Jordan canonical form. How will they be the key? Well, it will turn out that all we need to find will be bases for these generalized eigenspaces take the disjoint union of those bases, and that will give you the Jordan canonical basis. Okay, so it is enough to find basis for K lambda. Now, easy to say, but hard to do. I mean, who is this K lambda? We haven't computed any of them, right? It's just the null space of the mth power of some strange operator, right? Well, it turns out that the basis for K lambda have a very special form. They will be called, they will have the form of what will be called a cycle of generalized eigenvalues. A very specific format that you need to look at. So, next result tells you exactly what what I was saying before, that if the characteristic polynomial of T splits, lambda 1 through lambda k are the eigenvalues of T, distinct, with multiplicities m1 through mk. If beta I is an ordered basis for the generalized eigenspace k lambda I, okay, then any two such bases are disjoint. Right? So if you take a basis for k lambda and another one for k mu, where mu and lambda are distinct, then the bases do not overlap. If you take the union of all of them, you're going to form a basis for V. And in the end, the result that we've seen before, dimension of k lambda being less than or equal than m, in fact turns into equality when the characteristic polynomial of T splits. Right? So they are actually equal. So what happens, in fact, is this. So now, if the characteristic polynomial of T splits, that doesn't mean the operator T is diagonalizable, right? It could, or it may not be diagonalizable. But when T is diagonalizable, do you see what happens here? If T is diagonalizable, remember that that means the dimension of every eigenspace equaled the multiplicity of the corresponding eigenvalue, right? We had that theorem back then. So how could that be? E lambda and k lambda have the same dimension, being subspaces of each other, they would have to be equal. Okay, so this is kind of the extreme case. When the operator is diagonalizable, E lambda or K lambda is one and the same thing, and the matrix will turn into a perfectly diagonal form. In general, if T is not diagonalizable, E lambda would have a dimension that is less than m, which would be the dimension of K lambda. All right, so let's see how to find those bases, because this is the key here in the Jordan canonical form. How do you actually find those bases beta for k lambdas? Well, let's make some remarks. One. So let's say T is linear and generalized eigenvector for T. So X is a vector in k lambda with corresponding eigenvalue lambda. So there exists a positive integer n such that P minus lambda identity, so positive integer P raised to the P of X is 0. But now imagine that the number P is 3, right? Let's say it's 3. The third power of that thing applied to X is 0. It could also work for 4, right? Because I can apply T minus lambda identity to both sides, and I can raise that power as much as I want, right? I can apply it to 5 and to 100, right? But what is essential here is the value of the lowest value that this P can take, right? That's the important thing here. So I'm going to say that usually P will be just the smallest such number. It's easy to increase it, but it's not possible to decrease it. If it's the smallest, that means that the powers that are less than that, so the P minus 1 power, when applied to X, is not going to be 0 anymore, right? 2 less, if it's possible now, if I can subtract 2 from P and still get a positive integer, when applied to X, I'm still not getting 0, right? So it's the smallest number such that the power of T minus lambda identity applied to X gives you 0. X itself, I'm going to assume, is not 0, because otherwise all those values will be 0. I'm going to take all those vectors from X to the P minus 1 power and put them together in a set. So define gamma to be the set containing all those vectors from the P minus 1 power of that operator applied to X down to X itself. Again, because P was the smallest possible, gamma is a set containing non-zero vectors only. It is called a cycle of generalized eigenvectors. Corresponding to lambda. They are all corresponding to the same eigenvalue, lambda. So whatever we do for it, for one of these, we'll have to repeat for all the other eigenvalues then. We're going to, okay, corresponding to lambda of length P. P means there are P vectors in there, right, starting from the 0 minus 1 power. This one will be called the initial vector of the cycle. So the P minus 1 power is called the initial vector, and X itself is the end of the cycle. Now, this is called the cycle of generalized eigenvectors, because all those things, all those elements are generalized eigenvectors. Why are they all generalized eigenvectors? Well, take one of them, like T minus lambda identity to the power P minus 2. To show that this thing is a generalized eigenvector, let me move it to the right a bit. So for this to be a generalized eigenvector, it would mean that when you apply a certain power of T minus lambda identity to it, you get 0, right? What would that certain power be? Well, we constructed everything based on this assumption that the P power is 0. So here, I'm just applying the second power. So that will turn this into a generalized eigenvector. And I can mimic this idea, right? For every vector inside that set, I can find a certain number that I can raise T minus lambda identity to that to get 0. Okay, so they are all generalized eigenvectors. Precisely, so let's say note number 2. Exactly one vector in such a cycle is an eigenvector. An eigenvector. Do you see which one it is? What does it mean to be an eigenvector? Remember, it means that first power, right, when applied to that vector, gives you 0. An eigenvector, right, is a vector v such that t minus lambda identity of v is 0. Which power or which of those p vectors can I put in here to make it work? The very first one, correct. T minus 1 power. When you apply t minus lambda again, you're going to get the p power, which is 0. So that first initial vector, what is called, is an eigenvector. And it is the only one because there is no other vector in there with the property that when you just apply the first power of t minus lambda identity to it, you get the 0 vector, right? Remember that p was the lowest power with that property. Right, so when you apply t minus lambda identity, you just increase the power by 1, but you will never reach p again with any other vector. Okay. What does a cycle of length 1 mean? Because you'll encounter this a lot in the examples. P meant that you went from x to the p minus 1 power, right, of t minus lambda identity. Well, if p is 1, you don't go anywhere from x, right? You just have the vector x itself. Okay. But that also that the p power, right, when applied to x gives you 0 and p is 1. So t minus lambda identity of x is 0. But that again means exactly that x is an eigenvector. Corresponding to the eigenvalue lambda. Okay, so cycle of length 1 is the nicest thing that can happen. One eigenvector in there. Okay, so before we put everything together in some kind of theorem format, let me go back to the very beginning and make the connection a bit to those cycles. You know what will happen in this picture? This thing here and that thing there will correspond to cycles of length 1. Okay? This one here will be a cycle of length 3. And this one there will be a cycle of length 2. So that's how the connections will be between those spaces, those cycles, and the actual blocks. Okay. So now, we have a linear operator on a finite dimensional vector space. The only assumption is that the characteristic polynomial of t splits. Now, we're going to form a basis for V in such a way that for each generalized eigenspace and put them together, right? Take the union. But for each generalized eigenspace, the basis will consist of a disjoint union of cycles of generalized eigenvectors. Okay, so imagine fixing a lambda, right? An eigenvalue. Form the k lambda, the generalized eigenspace. The theorem says that the generalized eigenspace will have a basis that is in fact a disjoint union of cycles. Okay, that's the idea here. Well, it turns out that you form a Jordan block for each of those cycles. Okay, so as I was saying before, a cycle of length 1 gives you a Jordan block of size 1 by 1. A cycle of length 3 gives you a Jordan block of size 3 by 3, and so on. And this beta will turn out to be the Jordan Carnot basis. So here's the idea why everything works like they say. If I just take a cycle of generalized eigenvectors, I'm going to take, let's say, one of length p. And when I write this, I automatically mean that the next power, so the p power of x, will give you 0, right? And that's such integer. Okay, so this is the cycle. So let me call the vectors v1, vp minus 1, v sub p. And there are p of them. And I want to see what the restriction in this gamma looks like. I want to see what the block actually becomes. So I'm going to apply t minus lambda identity to the first vector, let's say v1. What do I get? 0, because that would give me the p power, right? Which the p power is going to be 0. But that means something that we've seen before, that v1 has to be an eigenvector. So t of v1 is lambda v1. I'm trying to create the block, the matrix. I'm just restricting everything to this little space, to gamma. So in this basis, v1 through vp, the first column looks like this. Lambda v1 and then zeros. I want to look at the second column, and to figure out what t of v2 is, I'm still going to apply t minus lambda identity to v2. Now v2 is the p minus 2 power, right? So when I apply t minus lambda to it, it becomes the p minus 1 power. But the p minus 1 power is v1. Right? Of x. Okay, so that means t of v2 minus lambda v2 equals v1. So t of v2, which gives me the second column, is in fact v1 plus lambda v2. I'm just reading the first and the last. Okay, but then the second column looks like this. 1, lambda, 0, all the way down. Let's do one more. Apply to v3. v3 is the p minus 3 power, right? The next one. P minus lambda identity of t minus lambda identity to the p minus 3 of x, which gives me t minus lambda identity to the p minus 2 of x. But the p minus 2 power of x is what vector? From gamma. Is the second vector there, right? v2. The p minus 2 is the one here. v2. Okay, so t minus lambda identity of v3 is v2. So t of v3 minus lambda v3 is v2. So t of v3 is lambda, well, it's v2 plus lambda v3. So what does the third column? 0, 1, lambda, and then zeros all the way down. Make sense? So this is, again, that's how the Jordan block is created. Let's look at the very last column. The very last given by t of the last vector, right? T of Vp. So I'm going to look at t minus lambda identity of Vp. Vp is just x. The t minus lambda identity of x is the previous vector, v sub p minus 1, right? So t of Vp minus lambda Vp is Vp minus 1. So t of Vp is Vp minus 1 plus lambda Vp. So the very last column looks like this. Zero, 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 1, lambda. Exactly a Jordan block, right? So every cycle that you get in that will create a block like this on the diagonal. Okay? What size of a block? Well, this is a p by p block. It's the size of the cycle that creates it. So this is again restating everything. If the characteristic polynomial splits, then T has a Jordan canonical form, which is formed by taking the union of bases for each k lambda. And you get that by taking a disjoint union of cycles. Okay? So again, what is the plan? So you're given a linear transformation T. You know how to find its eigenvalues, right? We all know how to do that. The characteristic polynomial splits, so you'll get a set of very nice eigenvalues with their multiplicities, right? For each of those eigenvalues, you need to find the corresponding generalized eigenspace for that, right? And then for each cycle in that basis, you throw a block in the Jordan canonical form, okay? That's the plan, but it's a bit shaky because we don't know how to get those cycles theoretically. So let's look into that. You see on page 495. Find the Jordan canonical form. Of the following matrix. -11, -4, -5, 21, -8, -11, 3, -1, 0. I could have started with a linear transformation instead, right? But then still that would create a matrix attached to it, so it's the same kind of idea. So step 1, find all the distinct eigenvalues of A. How do I do that? Well, I find the characteristic polynomial in the determinant of A minus T identity. can save some time by just stating or claiming that this is it. 1 plus t times 2 minus t, everything squared, is the characteristic polynomial of this matrix. So that creates two distinct eigenvalues. Lambda 1 equals negative 1 of multiplicity 1. And lambda 2 equals 2 of multiplicity 2. Okay. For every eigenvalue, I need to find the generalized eigenspace. And it's always nice to start with the eigenvalues of multiplicity 1. So I'll start with this one. Of multiplicity 1. Remember that the multiplicity is, in fact, the dimension of the generalized eigenspace, right? Each generalized eigenspace has the dimension equal to the multiplicity. So it must have dimension 1, right? But what dimension does it have? You know, the old eigenspace that we used to look at. It has to be 1 also. It cannot be 0, right? There should be something in there, and it's at most 1. But since they are equal in dimension, and they are subspaces of each other, the generalized eigenspace is nothing more than the original eigenspace, and we know how to deal with that, right? We know how to compute that. How do we do that? We just take the null space of t minus lambda, well, t, there is no t, a minus lambda 1, identity 3 by 3. Well, it's nice to notice that they are one and the same, right? E lambda and k lambda. However, it's not really necessary because if I find that theorem, here. K lambda in general is the null space of t minus lambda identity to the m power. M is the and multiplicity is 1, right? So the null space of t, or a minus lambda identity, which we know is the same as the regular eigenspace. So, same thing. All right, so this is the null space of lambda 1 is negative 1. A plus identity. So then you do 12, negative 4, negative 5, 21 minus negative 8 plus 1, negative 7, negative 1. 1, right? All right, x1, x2, x3, 0, 0, 0, and you solve that system, and you get that k lambda 1 and e lambda 1 are equal to the span of 1, 3, 0. So we found the basis for k lambda 1. It is a set containing a single vector, which is an eigenvector, right? It is a cycle of length 1, as we've seen before. So what kind of block will it produce in the Jordan canonical form? A nice 1-by-1 block that will have negative side, that eigenvalue that created everything here. Okay, so because of this, we'll throw a 1-by-1 block in the Jordan canonical form. Well, let's keep going. When the multiplicity is not 1, things are not so nice anymore. So the generalized eigenspace will now have dimension 2. Okay. So we're going to need to form a basis for that. But how can a basis look like for k lambda? Well, since the dimension is 2, and we know, from the theory that the basis for k lambda will always be a disjoint union of cycles, right? How can you get to 2 vectors? Well, there are 2 options. One single cycle of length 2, right? And that will be your basis. Second option, you have 2 disjoint cycles of length 1, right? That's the only way in which you can create 2 vectors out of a union of cycles. And at this point, you would have to be able to choose. Now, how do you choose? Well, what's the difference between 1 cycle of length 2 and 2 cycles of length 1? The difference is that the cycle of length 2 contains a single eigenvector, right, that initial vector. 2 cycles of length 1 in 2 vectors, right, 1 in each of them eigenvectors, correct? And linearly independent, so they form a basis together. So the second option here basically means that there are 2 linearly independent eigenvectors in k lambda. While option 1 means there is just 1. Now, how do I know whether there exist 2 linearly independent eigenvectors in k lambda? Well, if there are eigenvectors, and it's lambda 2 everywhere, right? K lambda 2. Eigenvectors actually belongs to the original eigenspace, E sub lambda, right? So if I find E sub lambda, which is something that I know how to do, that should tell me whether the second case is possible or not. So what I mean is this. Find E lambda 2, which is the null space of A minus lambda 2 identity, right? How do you find it? As before. So lambda 2 is 2, so subtract 2 from the diagonal. All right, and if you do this, you're going to obtain that E lambda 2 has dimension 1, and that's the basis. In particular, A is not diagonalizable, right? If we were to connect to chapter 5 now, because diagonalizable would mean the dimension of E lambda 2 must be 2. Okay, but because the dimension is 1, that means there is no way you'll be able to find 2 linearly independent eigenvectors corresponding to lambda 2. There is just at most 1, because if there were 2 of them, you could expand that to a basis, and it doesn't make sense. which eliminates the second option. The basis for k lambda 2 will not be the union of two disjoint cycles of length 1. Therefore, it must be the case that the basis lambda 2 consists of one single cycle of length 2. Gamma A minus lambda identity of x and x. Remember how you went up to the p minus 1 power? P was the length, p is 2. And the p power, the second power, when applied to x, should give you the 0 vector. X is non-zero. What we need to do now is find the vector x non-zero that has this property and such that the first power when applied to x is not 0 as well. How do I do that? Well, I'm going to start from here, compute the second power of this matrix. Apply to x. The second power, if I've done all the computations right in my notes, should look like this. So the second power, when applied to the vector x, should give you the 0 vector. And you're going to get that x2 and x3 are free. And x1 will depend like this on x2 and x3. x2 and x3 could be anything. You just choose one of them. You just need one vector, right? One non-zero vector. Choose whatever you want, but in such a way that hopefully, I'm going to make this choice. Let's say x2 is 1, x3 is 0. So I'm getting away with this vector, 1 to 0, which has this property here, that the second power applied to x gives you 0. All I need to check is this now, that the first power applied to x is not going to be 0. Okay? The first power applied to x is here. It could be 0 only if it belongs to the null space, and the null space was the span of 1, 1, 1. So as long as I don't make a choice of x that looks like in the span of 1, 1, 1, then I should be fine. So this one is clearly not. So you can check that a minus 2 identity of x is not going to give you the 0 vector. Okay, so almost done. So what is gamma in fact? X was 1 to 0. Other order, x was second, right? And when you apply a minus lambda identity to it, you actually get 1, 1, 1. And that's what will happen when you apply. Okay, so now, Jordan canonical basis is obtained by putting together all the bases for the generalized eigenspaces. You start with whichever one you want. If I start with this one, because I have it written here, I'll place both of them, and then I'll go back to the one before. For the other eigenvalue, it was 130, right? Throw that in. That's the basis. And the Jordan canonical form is the following. It's going to be a 3 by 3 matrix. This very last one came from the first eigenvalue. It was a 1 by 1 thing. So it's one block with entry the first eigenvalue, which was -1. That was because k lambda 1 had dimension 1. K lambda 2, which corresponds to those two vectors, has dimension 2, is going to, well, the basis was a single cycle of length 2. That means a cycle of length 2 creates a block like that. Yes?
Can we get
Backwards, you mean? Yes, but then you change the order in the basis. Yeah, if you move this one first, then the block will move on top. So you just follow the order from the basis. But up to that order, or disregarding that order, the Jordan form is unique. You're just allowed to move the blocks around. Okay, so again, this comes here because it was a cycle of length 2. If you had 2 cycles of length 1, let me use another color, then the matrix would have looked like this. Without that 1, it would have been diagonalizable because we kind of ran through that before. That was the reason it was not a union of 2 cycles of length 1. And again, because it's not, and it's a cycle of length 2, it's not diagonalizable, and it looks like that. Jordan canonical form. We'll probably see that is the final form.
There's not a 1 in the last one?
Which last one? No, because this is a block. 1 by 1 block, no 1 on top. Oh, I mean, everything else is 0, yeah. That's what I mean. The blocks are all that matter. We'll see more examples next time. I'll just stop.